and good afternoon, my dear invisible audience. Today, the talk I'm giving for this GEO-Wednesday event is a tribute to a great visionary and popular science author who is Jules Verne. And it happens that this year there are 150 years since he published his masterpiece, 20,000 Leagues Under the Seas. And in the background here you see the two maps that shows the voyage that the famous Nautilus submarine made in the Pacific and in the Atlantic Oceans. So I was inspired to give this talk by seeing this piece of news this summer in June 2020 that says on BBC that 1/5 of Earth's ocean floor is now mapped. This is a news prepared by the GEPCO 2030 project, which is a very big international project that started only a couple of years ago, and who have this great vision to cover with detailed data all our planet oceans with data. And this is what the project director said, that today we have mapped 90% and we have another 81% to map. And probably you have heard these analogies with Mars, that we know better how Mars is looks like, how the surface of Mars look like, but also so we still need to know about 2 times the surface of Mars, and which is the ocean floor of our own planet. So with this particular piece of news, we just become a little less ignorant about planet Earth. And I would like to inform you or remind you that starting next year, we will enter the United Nations Decade of Ocean Science for Sustainable Development. So it's a decade where scientists are called to get together and develop a scientific knowledge so we can know better about our oceans, because even without knowing what is about, we manage to harm this greater ecosystem on Earth, which is under the ocean. So just note that this decade aims to gather available and new data. So it's all about science. It's all about getting knowledge and to serve our community, both scientific and lay community, how to better manage 70% of the Earth's surface. And this is why they set these goals. And look at, this is all about getting a large database of data and knowledge. Is about information. It's about getting the ocean in the Earth system model, and it's about education. So educating the new generation and everyone about what oceans and seafloor means. So it's about getting together the science we need for the ocean we want. In today's talk, I would like to point a couple of things in these very dark areas here, which are the areas that we don't know too much. A lot of data and a lot of study has been done around continental margins, on continental shelves. This is also because this is where mineral resources are, like hydrocarbons, but we know very little about most of the oceans. And again, look at these dark areas in the Atlantic Ocean, in basically all oceans, Atlantic, the Indian Ocean, and the Pacific. So what you see in colors here are detailed bathymetry that was showing how the ocean is at meter scale resolution. And just to be clear, so I'm not going to talk about the ocean itself, the water, but what lays under the ocean, the oceanic basins. And this beautiful picture here shows that this interface between the water and life and ocean currents and the deep earth, this is the oceanic crust and the sediments that are the most unknown yet. So I'm going to talk mostly about the so-called brown ocean. And just going very briefly through a couple of how we can collect data, how we can know about what lays under the ocean. So the oceans are vast, are deep, and again cover 70% of our planet. So it's very difficult to go and look in person at what lays under the ocean. Therefore, we mainly use physics. So we use the properties of the material and use, for example, waves, all sorts of waves at different frequencies, whether they are sound waves or seismic waves, and try to see what lays under the water. And the first method that is widely used, and this is how the maps that I have shown before were made, is the so-called sonar. So a beam of sound or several beams of sound are sent from the hull of a ship to the ocean bottom, and they are sweeping basically with this sound and just looking at the time that takes the sound waves to go to the bottom of the oceans and come back. We can figure out the depth, but also the morphology of the ocean, and also the properties, whether it's soft sediment or harder rock. So this is how we can see the seafloor, how we can image the seafloor. But we can also use other type of waves, which are the seismic waves, and they are able to go to the seafloor and even deeper and bounce back by reflection, or even going deeper by refraction. And by doing this, we can image all sorts of layers that lay under the seafloor, the so-called sediments that were deposited for millions of years, and even go on top of the oceanic crust and even see volcanoes, buried volcanoes. So this is the so-called seismic method. Of course, we would like to know what kind of rocks and how old they are, what are their composition, but it's very difficult to get these rocks from the oceans. However, a wonderful and extraordinary international program called the International Discovery Program, or the International Ocean Drilling Program, has managed to get information, rock samples from all oceans during the last 4 to 5 decades. And this is a piece of core that has been retrieved from great depth. And we can take these rocks and analyze them in the laboratory and find out about the history of the ocean. And if we really want to go and measure very detailed a piece of seafloor, we can now send a lot of technology has developed all these automated unmanned vehicles. So there is less and less that the humans are going into these little submarines because the technology made this possible to get all these sensors on these submersibles that are going to the ocean floor and can take pictures, can take samples, can map the seafloor and also the water above it. But again, because the oceans are so vast, how can we know more about them by not going to every single locality and taking individual samples or images? And the answer is the satellites. So the community used satellites actually mostly during the Cold War in the 80s, and this is how this technology has been developed. But they become better and better. And this is an image of a satellite taken by a satellite in the 80s, where only very large tectonic features of the oceans could be mapped, so hundreds of kilometers. And then about 1 decade later, because more satellites were sent out, satellites are flying about 200, 300, 400 kilometers around the Earth. And here you can see the tracks, the satellite tracks, how they also evolved, and the distance between them became smaller and smaller. Therefore, we can get more and more information by just using satellites. So the satellite is using a radar pulse that is sent from the satellites, go to the sea surface and then go back again. The distance is measured, and because the sea surface is mimicking the seafloor, then this is how we can get all this information about the morphology of the seafloor. And in 1997, this is when I started my PhD, this wonderful map published by Smith and Sandwell in Science came out. And all of a sudden, it was this completely new world out there. So all these features in the oceans were now available for everyone to see and to map and to think about how they form, why are they important. And this is now the state-of-the-art map of bathymetry, which is using both satellite data, but also all the data that has been collected by vessels, by ships. And this is a map here showing in faint blue the tracks of ships that collected bathymetric data, so again the depth of the oceans. And this information plus satellite gave this new map released last year of bathymetry of global oceans that now reduce or increase the resolution from kilometers, tens of kilometers, to 500 meters, where we have this type of data. But most geodetic satellites are designed to fly around the Earth in the so-called sun-synchronous orbit, and because of this, and at a certain inclination, and because of this, you see it leaves a gap at polar regions, and this is the Arctic Ocean, which most of it is not well mapped by the satellites, and because we need data. So one piece of information actually was taken from submarine measurements, and this is a map showing the Arctic Ocean, and where all these tracks were made by submarine collecting data in the 1990s decade. And it's interestingly that actually it was the first nuclear powered submarine and the first submarine to go to the North Pole in 1958 that was called Nautilus, like the famous Nautilus submarine of Jules Verne, Nemo, that charted the world in the 19th century, in his story, of course. So what do we have now? We do have data from the satellites. We have local and regional data from echo sounders, but we can use much more information, and this is the rocks that forms the seafloor have a certain magnetization, so we can use the Earth magnetic field to know more about what lies under the oceans. And also, as I just said, this wonderful piece of data, which is the seismics that can see through the sediments and can see to the basement. So I will give you an example of how we have used this range of information and map seamounts in the Northeast Atlantic. So if you look at this map here, this tiny map here, and I'm not sure if you see, but there are tiny blue dots this is North Atlantic between Greenland and Europe. So tiny blue dots here and a couple of them here, but this area have only these red dots. So these are the seamounts, so basically huge mountains which sit on the seafloor, which were not mapped. And we participated in a project a couple of years ago, and this is where, by using all this information that I said, the bathymetry, then the gravity, where we can see these roundish or elliptical features on the seafloor, or the seismics, where we can see like cone-like features to map seamounts, or seamount-like oceanic igneous features. So we managed to map more than 400 seamounts by using all this remote sensing information. So I talked about Northeast Atlantic, and again, this is the latest map of bathymetry in Northeast Atlantic, and you can see Iceland here. You can see by these colors elevated, so shallow sea floor, elevated MidOcean ridges that go north and south of Iceland. And if we can continue along the MidOcean ridge, we see here that it's a big offset. And this is because this feature, the MidOcean ridge, this is the place where oceanic crust is formed for millions and millions of years, is offset, and is offset by the so-called fracture zone or transform fault. So these are extremely big scars in the oceanic crust. And these formed while the North America plate and Europe were departing from each other. And while they were doing this, they were forming the North Atlantic Ocean and forming the MidOcean ridge and these fracture zones. So these are spectacular features that are crossing all oceans. And again, look at the difference between the height of the seamounts of the MidOcean ridge flanks north of the Charlie Gibbs fracture zone and south. So it's a difference here. And they actually are highways of the oceans, and that's because they're extreme relief. For example, from top to down, there are about 2 kilometers of slope for the Charlie Gibbs fracture zone. So this is more than the Grand Canyon in the United States. And actually, if we go even south of the Atlantic Ocean, we go to the Romanche fracture zone, which has almost 8 kilometers of depth. So it's almost as deep as the deepest point in the oceanic floor. So fracture zones are immensely and very important features on the oceanic floor. And talking about fracture zones, I will take you to the Arctic Ocean, where we have used this information. Well, firstly, we have detected new fracture zones, and we have used this information to make sense of how an ocean was opened in the Arctic. And what I'm showing here, so this map, so this is the Arctic Ocean, which is north of Greenland and Siberia and Alaska and Barents Sea. And this part here is the oldest ocean in the Arctic. It's called the Amerasia Ocean. And this is an image showing the main features in this. So we can see the coastline, and we see this sinuous valley here that was detected several decades ago on satellite images. But this particular one, which is the latest satellite data or model that we have, they show here some segments in the MidOcean ridge, and maybe these features which could be dissecting this MidOcean ridge. And we know this is a MidOcean ridge because we can see it on the seismic reflection. We see this valley and flanks, which is exactly how a MidOcean ridge looks like. And we know that this is different from the previous satellite data has very faintly pointed to this particular type of segmentation. So when we looked closer to this part here, so here you see these segments which are intersected by oblique fracture zones, and we have then suggested that this ocean has formed at a specific spreading rate, and it was a spreading rate that went oblique and not perpendicular on the MidOcean Ridge. And this is our model where we have used also magnetic data. This is the MidOcean Ridge that is very much segmented based on the latest satellite data. And why this is important for us or for our understanding of the ocean basin is because, so if we look at how this part of the world looked like 150 million years ago, it was a lot of land here, so it's Europe and North America where all they were together, and this was the North Pacific. And the North Pacific had tiny, small oceans north of it. Once these oceans were closed, so then a new plate boundary, a new in the North Pacific formed, and this is when this force was triggering the opening of the Arctic Ocean. So it was the changes in the North Pacific that made an Arctic Ocean to open. So now I will take you to the youngest part of the Arctic Ocean, which is called Eurasia Basin. And here there are no fracture zones. And this is partly because this is the slowest spreading system in the world. And this is because this ocean is surrounded more or less by continents. So it's very difficult for it to expand, to grow. And this is the MidOcean Ridge, which and the flanks, which are very, very high, and the valley is very deep. And now I will take you to this part of the Eurasia Basin, which is the slowest ever ocean. This is the bathymetry, and it's full of sediments. And because it's so close to the continental margins, a lot of sediments were shed here. So it's very difficult to see what is under these sediments. But look at this particular hole. So in these sediments, it is a hole that doesn't allow the sediments to go there. And we looked with Russian colleagues, we looked at a piece of, again, seismic data, and we discovered that this is more than 5 kilometers deep and extremely wide for a valley of the MidOcean Ridge. This is probably the deepest part of the Eurasia Basin, if not of the entire Arctic. And interestingly enough, we have seen this pimple-like thing here, also in the seismic and also in the bathymetry. They were interpreted to be a seamount, so it's a volcano in this deepest part of the Arctic. And how come that a volcano is found its way here, where because this ocean spreads so slow, it is basically no new material that can come through the crust. And our explanation is the following. So in previous decade or so, the western part of the MidOcean region in the Arctic was characterized of being volcanic, and then a bit sparsely volcanic, and again volcanic. So this western part was well characterized, but not the eastern one. So now that we know that there are some seamounts and volcanoes in this part of the basin, we took a slice through the MidOcean Ridge here to 500 kilometers. So we have the possibility, we have data, again with seismic data, to image what lies underneath. And it looks like in here and there, so there are this hot mantle, this material that lies under the crust, that it managed to go into the MidOcean Ridge and forms volcanoes. So, okay, why should we really bother about these? Are wonderful stories, maybe for a small community of scientists who are interested in these old stories of how the Earth formed and how the ocean formed. But not only because Captain Nemo tells us that the sea is everything, but because actually what lies under the water is very important, not only to understand how the oceans form, what is the tectonics, but also to understand how the oceans, the ocean dynamics. And I will go back to the fracture zones again. So if you remember the Charlie Gibbs fracture zone, the biggest scar in the North Atlantic. And I said this is like a highway, and because of its impressive relief, it impacts a lot how the ocean currents flow around it. And it's again like a mountain, like the air, it's hitting a mountain and then it changes its course. And here it's a map of the North Atlantic current coming from the South Atlantic along the North American coast, and then all of a sudden you see it hits something, and then this is the Charlie Gibbs fracture zone, and it changes course. So it's now going along the Eurasia, the Europe's margin. Or look at the MidOcean Ridge. So we have here the MidOcean Ridge, these cold currents from the Northern Sea. They are deflected very much by the relief that is under the ocean. And not only the ocean currents, but of course life. It matters what is the relief exactly like on land. What is the relief and what kind of life can thrive there, and how this life can move from one part to another. And this is a very nice study published last year that took a lot of information and videos and images from 4 localities, which are north and south of the Charles Gibbs fracture zone, but also west and east of the Mid-Atlantic Ridge. And these are the 4 regions that are imaged, and they concluded by only looking at these images, but also doing more analysis, that it matters very much. So we do not have the same benthic communities north and south of the Charlie Gibbs fracture zone. And also the high relief, remember the very high relief north of the Charlie Gibbs fracture zone on the Mid-Atlantic Ridge. So it hinders these communities to go on the other side of the ridge. So again, it matters how the seafloor looks like and its relief. So I mentioned seamounts in the Northeast Atlantic, the one that we have mapped. Seamounts are littering basically the ocean floor. And just to give you an idea, there are thousands, hundreds of thousands, probably millions of seamounts. And they come in all sorts of heights and shapes. Here are a couple of examples from different oceans, and they are closer to the surface or deeply buried. And these are just the seamounts which were mapped, which are larger than 1.5 kilometers. These are intermediate, 1 to 1.5, and less than 1 kilometer. So you see literally littered by seamounts. And by the way, the highest mount on our planet is not Mount Everest, but actually is Mount Kea, which lies a great deal under the sea. So seamounts are geologically and biologically hotspots that connect lithosphere, hydrosphere, and biosphere. And only counting the large seamounts, this biome is larger than the biome of Europe. This image shows how a seamount has an impact on the ocean circulation. So you see it's this blue here. It shows that the ocean are much more dynamic and a lot of motion. Up to 800 meters, so at least the top 400-500 meters of the seamount impact a lot the ocean circulation, and because of this, of course, the plankton or other life is able or enabled to go from the surface to the deep. So just to make this very simple, they are major passageways for fluid circulation, for different geochemical elements, and last but not least for life. And this is a nice cartoon here showing how different type of life can be found, from macrofauna to microbes on the seamounts. So all these mid-ocean ridges, fracture zones, seamounts, they make the seafloor very rough. So it's not like a beach, which is very nice and smooth. And this map show the part of the oceans which are very, very rough here in these colors. And again, this information can be extracted from the global image that the satellites give us. For example, if we look only at the data that is given by ship track bathymetry, we have this very blurry and very low resolution image of the seafloor, but when we take the satellite information, you see all these fracture zones, and the fabric of the seafloor comes much clearer. And if we take this profile here through the smooth and rough oceanic crust, we see that on top of the smooth seafloor we have stratified oceans, and on top of the rough seafloor it's a mixed ocean. So this is an image of the vertical diffusivity of water. And just to make a bit of publicity of another project in our department, so this is called the so-called the Rough Ocean, financed by the Research Council, and with the PI, Professor Joe Lacasse, where the idea is to look at how bottom topography affects oceanic flows, and especially in the North Atlantic. So, for example, how it affects the Gulf Stream. Another interesting and important process or events that happened at the bottom of the sea are volcanoes. And there are, as you have seen, a lot of seamounts. Of course, not all of them are active. The one closer to the MidOcean Ridge are active, but not only. There are also intraplate volcanism. And this, for example, is an image from the deepest known underwater volcanic eruption that happens at more than 4 kilometers in the Pacific. And as I said, there are a lot of volcanoes active along the mid-ocean ridges, and this is how the seismicity that is, because some of it is because of volcanism. But also this volcanism impact the evolution of the seawater chemistry in time. And what we did a couple of years ago, we looked at how fast or how much of these volcanoes were evolved into oceanic crust. And this is, for example, where you see red, this is the young oceanic crust. And the young oceanic crust is usually more porous, so it can interact with water, and then it can has a great influence on its chemistry. So the more volcanoes you have, then the more calcitic the oceanic water is, and the less then is the more magnesium. And because of that, we have the so-called calcite and aragonite oceans. So right now we are in aragonite type of seas. And of course, this is very important because the change of chemistry of the oceanic, of the seawater has a big impact of what type of organisms are developed in the oceans. And particularly on reef-building organisms. And last but not least, volcanism, hydrothermal activity, and seafloor alteration. They have a big impact of what kind of rocks are formed on the seafloor through time, and many of these rocks now are considered mineral resources. So more and more the humanity is looking at what we can, what type of minerals we can gather from the seafloor. And here I'm showing this map with these patches in different colors, showing polymetallic nodules in blue. So they are mostly on old oceanic crust, and they are forming because of precipitation of different minerals. Massive sulfide, they are mostly at where the new oceanic crust is formed along the mid-ocean ridges, and they are full of important minerals, but also cobalt-rich ferromanganese crust in yellow. So the seafloor has a lot of potential for mineral resources, and of course we have to be careful how we map this, what knowledge we get, and make sure that if we use that, we do not destroy the habitat that is closely related to this ecosystem. Of course, this is not something that was discovered recently. It has been around from the 60s. This is a paper from the Scientific American in 1960, where it says that the depths of the ocean are strewed with curious nodules that are rich in manganese, copper, cobalt, and nickel. But in the last decade, it is really a quest to map more and more, and even to apply for licenses to mine these resources from the seafloor. Norwegian government announced 30 million to map the minerals from the ocean floor. Of course, this is not too much, but this is just the beginning of these activities. So what is the way forward? Of course, that we have learned a lot in the last 150 years, in the last 50 years, or even in the last decade. But as you can see, there are big holes in our knowledge. Of course, we need more data. We always need more data. But importantly, there are a lot of archives which are not available to the society, to the community. And this is what this GEPCO 2030 aim is. They are not basically putting a flotilla of vessels to map now the whole oceans. They are asking everyone who has data to contribute with it. But of course, we need smarter way to make sense of the data we have, of the knowledge. And what is also very important is to bring awareness to the society, to the new generation, to everyone, how important the oceans, and not just the oceans, but what lies beneath. And what we do, the little that we can help from University of Oslo, especially that we do not have access to research vessels for different reasons, particularly because we are not facing the North Atlantic directly. But anyway, we are using these wonderful open source type of databases that we can get our hands on. Especially, we are very much interested in the Arctic Ocean and in the North Atlantic. And lucky us, as you can see here, there are not that many black holes. And just to mention here a couple of projects that my colleagues are involved. One is looking at the biggest seamount in Northeast Atlantic. It's called the Vesteri Seamount. Another one is looking at the Jan Mayen fracture zone, basically the only fracture zone in the Northeast Atlantic, that it's a very interesting barrier to ocean currents, but also probably to the mantle. And another piece of information here, that we are also engaged in a wonderful project that is financed by the European Research Council, and this a lot of people from the mathematical natural science faculty are involved. Is called ComSci, Training in Computational Science. And what we want to do with my colleague here, Clint Conrad, is to look at these wonderful images of seamounts, or data that can give us the information about seamounts, but do this in an automatic way, in a more intelligent way, and map this. So this is a PhD project that will become available next year. So we do need to know more about what lies under the oceans, because who knows, maybe that will be our next home. And again, it's not only because Jules Verne told us that it's wonderful to take energy and everything you need from a seamount, but also people here in Oslo are dreaming about living under the sea. These are arts taken from the Oslo Frø and T-bane, and as you can see, we have submarines, we have people going under the sea, and also houses built there. So with this, thank you so much for attending this online lecture. And if you have any questions, I would be more than happy to answer them. This is my email address. Thank you very much.
Thank you very much, Carmen, for taking us into this very interesting journey about the importance of the seafloor and all the implications of that. And as you said, questions can be sent directly to your email. And this is the last GEO-Wednesday before Christmas. We take a Christmas break already. We meet again in January, and I will particularly thank the Science Library for the cooperation and for helping us to have this GEO-Wednesday. So thank you to all that has been here listening to Carmen today, and welcome back after New Year.